Example 6. We have a particle P that moves along a straight line such that its displacement x from the origin is given by x equals to 11 plus 6t squared minus t cubed. T is measured in seconds, measured from the beginning of motion, and we want to calculate a number of things. So we can see that in the question we are going to be dealing with both velocity and acceleration at some point in time. So it's a good idea that before we even start the questions, right, that we take the displacement time function, right, we differentiate twice for the velocity time and acceleration time functions. So that's essentially how we're going to start. Okay, so take note, we are given that x is equals to 11 plus 6t squared minus t cubed. If I differentiate this, I'm looking at x dot is equals to, differentiate 11, I get nothing. Differentiate 6t squared, we get 12 times t. Differentiate minus t cubed, we get minus 3t squared. If I differentiate this again, we're looking at x double dot is equals to 12 minus 6t. So given these functions, right, part 1, we want to find the velocity of p after 3 seconds. So the velocity of p when t is equals to 3, right, we can clearly see that x dot is just going to be equals to 12 times 3 minus 3 squared. And that's going to give us 36 minus 27. So we know that when t is equals to 3, its velocity is 9 meters per second. Then in part 2, we want to find the velocity of p when the acceleration is equals to 0. Okay, so let's find out when the acceleration is equals to 0 first. So if I let x double dot, okay, which is acceleration, be equals to 0, acceleration is given by 12 minus 6t. So if I take 12 minus 6t and I solve this to be equals to 0, it's quite obvious that t is just going to be equals to 2 in this case. So we know that acceleration is equals to 0 when t is equals to 2. So if we want to find out the velocity at this point in time, just take t equals to 2 and substitute it back into the velocity time function. So when t is equals to 2, we can clearly see that x dot is equals to 12 times 2 minus 3 times 2 squared. And that's going to be equals to 24 minus 12, okay, which is just 12 meters per second. Okay, so that's all we have for part 2. Now then part 3, okay, we want to find the average velocity of p in the first 2 seconds. Now in order to calculate average velocity, recall that average velocity is equals to, so this is part 3, recall that average velocity, okay, is equals to the change in displacement divided by the change in time. Okay, so that's essentially the definition that we have for average velocity. Some people, right, might be misled into thinking that because it's the average, okay, we can look at the initial velocity, okay, which is the velocity when t is equals to 0, and then the final velocity at t is equals to 2, and add the two together and divide it by 2 in the traditional sense of the word average. But that's not going to work, okay, especially not when our acceleration is a nonlinear function, right? Because you guys can see when we differentiate it here, acceleration is given by 12 minus 6t, so acceleration is changing all the time. So the idea here, okay, initial velocity plus final velocity equals to 2 will give us the average velocity if acceleration is always a constant, okay, or in other words, what we call uniform motion. But in math, okay, so usually these misconceptions come from people who do physics, okay, but in math, when we're dealing with non-uniform acceleration, then what happens is that's not going to be the case. So in order to find the average velocity, let's look at the displacement time function. Okay, so the displacement time function is given by x equals to 11 plus 6t squared minus t cubed. And we can clearly see that when t is equals to 0, x is equals to 11, right? Because all the t's become zeros. And then when t is equals to 2, our x value is equals to 11 plus 6 times 2 squared minus 2 cubed. So that's going to give us, if we just type everything into the calculator, an x value of 27. So the change in displacement, we go from x equals to 11 to x equals to 27. So the change in displacement is 27 divided by 11. And the change in time, okay, just 2 minus 0. It occurs over 2 seconds. So in this particular case, the way in which we should set this out is average velocity is equals to final displacement minus initial displacement divided by change in time interval. If you check this out, 27 minus 11 is 16 divided by 2. So our average velocity is therefore going to be positive 8 meters per second. So with this, okay, part 4, we then want to find the acceleration of the particle p as it reverses its direction. So a particle reverses its direction when x dot is equals to 0. Okay, not always. X dot equals to 0, what that describes is when the particle is stationary. Okay, the particle doesn't have to reverse direction at x dot equals to 0, but every time it reverses direction, x dot will be equals to 0. Okay, so in other words, it's a necessary condition. For example, if we have, say, a number line, right? We've got a particle moving on this number line. Say my particle is initially moving towards the right in the positive direction. And then what happens is that in order to reverse direction, okay, it needs to move towards the left, right? So it's moving towards the right, and then it needs to slow down over time, and then it needs to come to a stop before it reverses direction. This has to happen. Of course, when it comes to a stop, it might not choose to reverse direction, okay? It could just be a particle moving towards the right, okay? And then it comes to a stop, takes a rest, and then begins moving to the right again. That could be the case. But if you want a particle that was moving to the right, okay, and then all of a sudden you want it to move towards the left, okay, the transition must be gradual in the sense that the particle that was initially moving towards the right, it must be slowed down over time, come to a stop, and then reverse direction. So whenever we're looking at a particle reversing direction, it always needs to satisfy x dot equals to 0, okay, because it needs to come to a rest before it can reverse direction. So having said that, okay, we know that x dot is given by 12t minus 3t squared. So using this, right, we can now come along. So this is part 4, right? We know that x dot is equals to 12t minus 3t squared. And we're going to let x dot equals to 0, right, to see when the particle is at rest. When particle is at rest, and solving 12t minus 3t squared equals to 0 is fairly easy. We start by factorizing 3t out, and we've got 4 minus t left over, okay, equals to 0. We can say that t is equals to 0 and t equals to 4 are the solutions of this equation. So these 2 points in time, what they represent is when the particle is at rest. The question is specifically asking for when the particle reverses direction. Now, I will not count t equals to 0 as when the particle is reversing direction. I'll say that the particle is at rest at this point in time, sure, okay, but the particle does not reverse direction at t equals to 0 because this is the beginning of motion. If you want to say that the particle reverses direction, you need to be able to inspect the motion before this time period and after this time period to actually show that the direction has changed. We have nothing to compare for negative values of t, so therefore this would not be applicable as an answer, okay, if we're looking at reversing direction. So particle does not reverse direction, does not reverse direction at this point in time. Okay, this is just an interpretation for this particular solution. Again, this is how I interpret this value. As for t is equals to 4, just to demonstrate this idea very, very briefly, okay, what I'm going to do is I'm going to draw up a table of values, and then I'm going to look at t versus x dot. Okay, x dot is velocity. It tells me the direction in which the particle is moving. So when we look at this, t is equals to 4, x dot is equals to 0. And let's take a look at t equals to 3 and t is equals to 5. So when t is equals to 3, okay, we can see that x dot is going to be 36 minus 27. So that's going to be positive 9. I'm just going to take note that velocity is positive at this point in time. When t is equals to 5, we're looking at 60 minus 3 times 25. So 60 minus 75 is negative 15. So we're going to take note that velocity is negative. So what this indicates for us is that the particle is initially moving towards the right, so my displacement is increasing. It comes to a stop, and then my velocity becomes negative, which means that the particle is now going the other way. Okay, so displacement increases, it stops, stationary point, and then it reverses direction, okay, by moving towards the left. So we can see that t is equals to 4 is when the particle reverses direction. And this kind of proof is also valid if the question is asking for something like find when the particle reaches maximum displacement. Okay, this would be what maximum displacement looks like. Particle is moving towards the right, it reaches the maximum displacement, and then it reverses direction. Okay, so observe that this is also valid, okay, as proof if the question is asking for maximum displacement. This is just as an extra for note if you guys ever need anything like this, which you will, depending on the question, okay? So if that's the case, right, coming back to the question, we want to find the acceleration of the particle as it reverses direction. So we know that x double dot is equals to 12 minus 6t. So naturally, when t is equals to 4, x double dot is going to be 12 minus 24, which is negative 12 meters per second squared. And that's all we've got for part 4. Fairly simple. Now then for part 5, we want to find the position of P after 5 seconds, and we want to find the distance that P covered in the first 5 seconds. So if I want to find the position of P after 5 seconds, that's fairly easy, right? We've got the displacement time function, which is given by 11 plus 6t squared minus t cubed. So let's start off with the displacement time function. So part 5, we know that x is equals to 11 plus 6t squared minus t cubed. So when t is equals to 5, we can clearly see that x is equals to 11 plus 6 times 5 squared minus 5 cubed. And what that's going to turn out to be equals to is just x equals to 36. So that's going to be the position of the particle, okay, at t is equals to 5. So now if I want to, then in part 6, find the distance that P covered in 5 seconds, what do I do now? A lot of the times people start off by considering, we know that when t is equals to 0, x is equals to 11. And then when t is equals to 5, right, we just found that x is equals to 36. And then they go, okay, so from the beginning of the motion to when t is equals to 5, my x value changed from 11 to 36. So then they go, okay, the changing x is equals to 25, and then go, okay, that's the distance traveled. Not necessarily so. What you guys have to be aware of, okay, in these cases is remember that displacement and distance are not necessarily the same thing. Okay, I mean, they are conceptually different, but the value that you get when you look at distance and displacement aren't always the same. And the trick is to ask yourself, does the particle reverse direction, right, at some point during its motion? So if it does, then obviously we have a problem. So for this particular question, we know that for the earlier part, okay, just right here for part 4, we know that the particle reverses direction at t is equals to 4, and we showed it. Okay, at t equals to 4, the particle is at rest. Before this point in time, the displacement is increasing. After this time, the displacement is decreasing. So the idea here, okay, if I was to draw this out just to show you guys what this displacement time function actually looks like. So say I've got x versus t, okay, this is very roughly speaking, okay, so I'm not doing anything to scale. This cubic, just take my word for it. I mean, you guys should all be able to sketch this if you do some calculus. This is a negative cubic, and you've got a stationary point at t is equals to 0 and at t is equals to 4. Okay, how do I know that? Because in the previous part of the question, we found when x dot is equals to 0. X dot is equals to 0 when t equals to 0, and x dot is equals to 0 when t is equals to 4. Okay, so that's essentially when your particle was stationary. So here, we know that when t is equals to 0, x is equals to 11. I dotted this part out on the left because it's not necessary. So what is happening here is that the particle starts at x equals to 11, and initially it's at rest. And then it starts moving in the positive direction. Once it's at t equals to 4, we don't know the displacement quite yet. So now let's check that out. Okay, so just as an extra, when t is equals to 4, my x value is going to be 11 plus 6 times 4 squared minus 4 cubed, and that's actually going to give us x equals to 43. Okay, so that's going to be this stationary point right here. Okay, that's going to be 43. So the particle, okay, if I draw this on the number line, some people prefer looking at the number line. My particle starts at x equals to 11, and then from 11, my x value increases towards 43, right? So I have moved from x equals to 11 all the way to x equals to 43, and that took 4 seconds. And then afterwards, we said that the particle reverses direction. And we can see that because when t is equals to 5, we realize that x is actually equals to 36. So not drawn to scale. Let's say that this is t is equals to 5. And we know that x is equals to 36. So what has happened here is from t equals to 4 to t equals to 5, my particle reversed direction as we have shown in part 4. And we can see that when the particle reverses direction at t equals to 4, it then moves towards the left. Okay, so that at t equals to 5, it reaches x equals to 36. Right, so that's x equals to 36. And then we can see that the motion of the particle is now in the negative direction. And it goes from 43 back to 36. So if we're looking at the distance traveled, okay, the distance traveled should incorporate from x equals to 11 to x equals to 43, and then from x equals to 43 back to x equals to 36, right? So in other words, the distance traveled, okay, the distance traveled should be equals to, now 11 to 43, that's going to be 32 units to the right, and then from 43 back to 36, that's 7 units towards the left, right? Distance, we don't care whether it's to the right or to the left, we're just looking at the numerical values. And 32 plus 7 is equals to 39 units, right? So that is essentially the way that we calculate distance. And sorry, this is actually measured in meters. So I will change that. So it's actually 39 meters, right? This is not the same as displacement, right? If we were to look for the change in displacement, that's just looking at the initial position, the final position, and say, well, hey, I've gone from 11 to 36. So the change in position, right, is I have ended up 25 units to the right of where I've started, but that's not the case. Okay, so the distance traveled is more complex. And the best advice I can give you guys, okay, for when you guys need to pay extra attention to this kind of thing is when you're doing distance kind of work, ask yourself, does the particle change direction? Okay, change direction during its motion. If it does, okay, which indicates that when the particle is moving towards the right and then it moves, okay, in the other way and it moves towards the left, then in those cases, we must separate out the motion in order to find the distance traveled. Okay, of course, if the question just wants the change in displacement, that's always easy. But the distance traveled, okay, that's a little bit of a different story. So take note, okay, have a think about it, see if everything makes sense, but you need to understand this, okay? There's a fundamental difference between distance and displacement. Now, that being said, this is all we've got for example 6.